Look up at the night sky. What do you see? You see a beautiful tapestry of twinkling lights. Some are bright, some are faint, some are scattered like dust across a black velvet cloth. For thousands of years, humans have looked up and wondered, what are those lights? And more importantly, how far away are they? It seems like an impossible question to answer. After all, we can't just stretch out a giant tape measure into space. We can't send a spaceship to a distant galaxy and check the odometer. The universe is vast, far bigger than our minds can truly grasp. The distances are so enormous that our everyday units of measurement become almost meaningless. Imagine you are standing in a completely dark field. Someone is holding a candle. If the candle is very bright, you might think it is close to you. If it is very faint, you might think it is far away. What if you knew for certain the exact brightness of that candle? Then you could measure how bright it appears to you, and use a simple formula to calculate exactly how far away it is. This is exactly what astronomers mean by a standard candle. It's any astronomical object that has a known, consistent, and predictable level of brightness. If we can find these special objects scattered throughout the universe, we can use them as reliable distance markers. Our journey begins not in a grand observatory with a famous male astronomer, but in a quiet room at Harvard College Observatory in the early 1900s. It begins with a woman named Henrietta Leavitt. In an era when women were largely barred from professional astronomy, Leavitt was hired as a computer. Her job was to examine photographic plates of the stars, paid a mere 30 cents an hour. Leavitt was assigned to study the stars in the Magellanic Clouds. These are two fuzzy patches of light visible from the southern hemisphere, now known to be small satellite galaxies of our own Milky Way. As she worked, a remarkable pattern began to emerge. She noticed that the brightest Cepheids took longer to complete one cycle of dimming and brightening. The fainter Cepheids pulsed much more quickly. The full power of Leavitt's discovery was unleashed by Edwin Hubble. In the early 1920s, Hubble was using the brand new 100-inch Hooker telescope, then the largest telescope in the world. He turned this powerful eye toward the great Andromeda Nebula. In October 1923, he found a Cepheid variable star within it. This would resolve the great debate once and for all. Using Leavitt's period luminosity law, Hubble calculated that the Andromeda Nebula was nearly 1 million light-years away. This proved that it was not a nearby cloud, but a colossal galaxy just like our own. The universe was not just one galaxy. It was filled with them. Our entire conception of the cosmos was shattered and rebuilt in an instant. To build a ladder that can reach across the cosmos, you must start with a solid base. The first rung uses parallax, the same principle you use when you hold your thumb out and blink from one eye to the other. Once we measure distances to nearby stars using parallax, we can calibrate our Cepheid variables. This creates the second rung of our cosmic ladder. To probe deeper into the cosmos, we need even brighter candles. Type Ia supernovae are the ultimate standard candles, explosions so bright they can outshine an entire galaxy of billions of stars. These explosions occur when a white dwarf star reaches a critical mass limit. Because this trigger is so precise, every Type Ia supernova releases nearly identical amounts of energy. It was by using Type Ia supernovae that astronomers made the shocking discovery in 1998 that the expansion of the universe is accelerating. This led to the discovery of dark energy. This tells us that about 70% of our universe is made of a mysterious, anti-gravitational force that we do not understand at all. Today, we face the Hubble tension, a major disagreement between two trusted methods for measuring the universe's expansion rate. The local measurement gives 73, while the early universe method predicts 67. This 9% difference is not a small disagreement. It suggests that either our standard candles aren't as standard as we think, or there's new physics we haven't discovered. To push forward, we are building ever more powerful tools. New telescopes like the James Webb Space Telescope and the upcoming Vera Rubin Observatory will measure standard candles with unprecedented precision. The quest that began with Henrietta Leavitt counting dots on a photographic plate continues with fleets of robotic telescopes surveying the entire sky every night. Standard candles have transformed our understanding of reality. They revealed a cosmos far stranger and more wonderful than we ever could have imagined, taking us from cosmic ignorance to profound understanding. The simple act of measuring brightness has unlocked the deepest secrets of the universe. They are the lighthouses that have guided us across the dark and unknown cosmic ocean, and they continue to point toward the next great mystery.